Hello everyone, my name is Dina Lestari and I'm a final year student at Universitas YOLO in Indonesia. It is such an honor to be part of this conference. I would also like to greet all participants and presenters. Thank you for sharing your insights and work in this valuable forum. Today, I will present my study titled A Survey on Deep Learning Best Approaches for Tomato Ripeness Detection. This paper is collaborative work between Universitas Girimangi and UIN Sunan Gunung Jati Bandung, and it focuses on the use of deep learning object detection methods in agriculture, especially for tomato ripeness detection. This presentation is structured into six main sections: introduction, background, methodology, deep learning technique, and observation. And the last one, where we can talk about key challenge and future work. So I will begin with the context and motivation, followed by the technical and analytical components of the survey. The first one is the post-harvest loss and role of the eye. Every year, about 20 to 30% of fruits and vegetables are lost if they're harvested due to improper timing and inaccurate ripeness detection. Tomatoes are particularly affected. Their ripeness level determines market value, taste, nutritional quality, and shelf life. To address this issue, recent developments in automation, sensors, and artificial intelligence have supported more efficient ripeness detection. Among this, deep learning combined with computer vision offers promising results in interpreting image best for agriculture data. So my study have a focus on deep learning methods applied to object detection tasks for tomato ripeness classification. The models we surveyed include CNN-based detectors and transformer detectors. For CNN-based detectors, we study such as YOLO, SSD, and faster RCNN. So for the transformer-based approaches, we study for the visual transformer or FIT and GETR. These models are commonly used due to their ability to localize and classify tomato ripeness levels directly from images. And this is the numbers of pepper per year in a range time 5 years. We study the peppers have a lot on 2022. So we have a contribution of this study has a three contribution. The first one is reviewing existing datasets and evaluation metrics used in tomato ripeness detection, such as MAP or mean average precision, recall, and frame per second or FPS. The second one is comparing the performance of several deep learning models used in previous works. And the last one, to identifying open challenge and proposing possible direction for future research. And this is the background about the study. Traditionally, object detection used handcrafted features, including HOG and SIP, combined with sliding window classifiers. These methods were often inefficient and less accurate. In 2012, the introduction of CNN-based models like ResNet marked a breakthrough, offering automatic feature extraction and much higher performance. This led to widespread use of deep learning in object detection, including for agriculture application like tomato ripeness detection. Models such as YOLO and faster RCNN have shown significant improvements in both accuracy and computational efficiency. This study is conducted as a systematic literature review or SLR. The methodology involves a structured research, selection, and analysis process, which I will explain in this slide. So the study addresses four main research questions. The first one is what deep learning models are used in tomato ripeness detection? And the second question is what are the characteristics of the datasets? And the third question is, what metrics are commonly used to evaluate model performance? And the last question, what are the major challenges in this area? We use keywords such as tomato ripeness detection, YOLO, and CNN in agriculture, and selected articles from IEEE Explorer, Science Direct, Springer, and GPI, and Google Scholar. Following the Prisma framework, 50 studies published between 2015 and 2025 were selected for in-depth review. So in this session, I'll briefly describe the deep learning architecture most commonly used in tomato ripeness detection. Deep learning-based object detection separated by two bases. The first one, CNN base, and the second one for transformer base. The deep learning technique used are categorized into three groups. CNN-based models has a example like YOLO. This is the real-time detection widely used in agriculture. And the second one is faster RCNN, two-stage detection with high accuracy. And the ResNet and VGGNet known for robust and feature extraction. So for the transformer-based models, has a fission transformer or FET, capture global feature effectively, and detection transformer or DATR models relationship across the full image spaces. And the hybrid or enhanced model, this often integrate attention mechanism to improve performance in challenging visual conditions, such as occlusion or cluttered scenes. Here are some comparative results from studies included in the review. For example, FIT achieved 98.67% accuracy in a greenhouse environment, outperforming CNN-based models like ResNet and EfficientNet. Hybrid models such as SETR and SegFormer also perform well, though not as high in accuracy. So for the key observation from the literature include YOLO remains widely used due to its speed and acceptable accuracy for real-time tasks. Many datasets were captured in controlled environments such as greenhouse. This result is environmental bias. For the lighting, cultivar type, and subjective annotation also contribute to dataset limitation. To improve model generalization, that datasets should be captured in diverse environments, include various tomato varieties, and have expert verified annotation. Despite progress, several challenges remain, like the first one, lack of dataset diversity and presence of annotation bias. Second one, trade-off between high accuracy and low computational demand, especially for edge devices. And the last one, inability to handle occlusion or complex scenes effectively in real-world conditions. So for the future work, directions include first, designing lightweight models such as YOLO P11 and YOLO P12, or EfficientNet variants for real-time deployment on low-resource devices. And second, applying attention mechanism to improve object localization in challenging scenes. And the third, building more diverse data sets representing real agriculture data condition like outdoor fields, multiple cultivars, and variable lighting. And the last one, combining CNN and transformer architecture may also improve model robustness and accuracy. To conclude, deep learning-based object detection offers a promising solution for improving tomato ripeness detection in agriculture. This survey presents the current landscape, identifies critical gaps, and suggests future directions toward building more accurate, efficient, and reliable system. Thank you very much for your attention. I welcome any questions or feedback you may have.